Hi, today is Wednesday, December 3rd, 2025. It's already Wednesday, hump day, and third day of this month. Later this afternoon, around 5:30 or 5:40, before the normal work end hour of 6 o'clock, our team, our entire office will go to a restaurant and have a sit down and celebrate the year end by eating nice food. Still, there are many more days left before the end of the year, but since we Koreans have many clubs or organizations, associations, or get togethers with friends, colleagues, acquaintances, family members, we would be getting busy with a lot of year-end parties. So my office decided to have one today. All the foods would be free, and there would be some booze, imbibing, drinking alcoholic beverages. But as for me, maybe I'll just sip beer and in a very small cup, just as a token of being with them and being present at the moment. Today we are going to learn about CPU, GPU, and TPU. And we are going to learn technical terms about in English, right? And we have to read English materials on a daily basis to practice English. Even though I'm getting old and getting to the age where I have to retirement age, I am very interested in learning foreign languages, including Chinese, and English. And also I learned German in high school. Of course, I forgot almost all of them. We, as a non-native speaker, need to practice English every day or for at any opportunity that we can find. So this is purely academic effort. If you are listening to my video, just stay tuned and see what pronunciations I am good at and I am poor at, and what your opinions are regarding my reading speed, pronunciation, or the understanding of the context. I would be happy to accommodate your input. This article is from databasemart.com, and the title is CPU versus GPU versus TPU, Key Differences, Use Cases, and Performance Explained. The rapid growth of artificial intelligence, data analytics, and cloud computing has created a demand for increasingly powerful computing hardware. While traditional GPUs, central processing units, remain the backbone of general-purpose computing, the rise of GPUs, graphics processing units, and TPUs, tensor processing units, has reshaped how we process data, train AI models, and deploy applications at scale. Each of these processors has unique strengths. CPUs excel at versatility and complex logic. GPUs are designed for parallel workloads like graphics rendering and AI training, while TPUs focus on accelerating machine learning with specialized tensor operations. So that's why the word tensor came from, right? Tensor operations. So basically, CPUs excel at versatility and complex logic. GPUs are designed for parallel workloads like graphics rendering, not graphic rendering, but graphics rendering, and AI training, while TPUs focus on accelerating machine learning with specialized tensor operations. GPU hosting. What is a CPU, Central Processing Unit? The CPU, often called the brain of a computer, is the primary processor responsible for executing instructions and managing general-purpose tasks. It is designed to handle a wide variety of operations, from running operating systems and applications to controlling hardware resources. Key characteristics of a CPU: few cores, high clock speed. CPUs usually have fewer cores than GPUs, but each core is optimized for powerful single-thread performance. Complex instruction sets capable of handling diverse and complex tasks, including arithmetic, logic, memory management, and input-output operations. Low parallelism. High flexibility. Unlike GPUs or TPUs, CPUs are not built for massive parallel workloads, but excel in versatility and general-purpose computing. Strengths of a CPU: handles sequential and logic-heavy tasks efficiently. That's a good expression, right? This one, right? Logic-heavy tasks. Logic-heavy tasks. Essential for running the operating system and coordinating hardware. Well suited for small-scale AI inference, business applications, and everyday computing. Limitations of a CPU: not optimized for large-scale parallel processing, slower in workloads like deep learning training compared to GPUs or TPUs, higher cost per unit of compute power for specialized tasks, for example, AI training. Use cases of CPUs: running operating systems and everyday software, browsers, office apps. Server-side tasks like web hosting, databases, and transactions. Here, server-side tasks or public-facing operations, customer-facing operations, or business-facing operations are totally different, but server-side tasks. Orchestration in heterogeneous computing system, GPU plus GPU/TPU collaboration. What is a GPU? Graphics processing unit, not graphic processing, but graphics processing unit. A GPU or graphics processing unit was originally designed to accelerate the rendering of images and graphics for displays. Over time, GPUs have evolved into powerful parallel processors capable of handling large-scale mathematical and scientific computations, especially in artificial intelligence and deep learning. Key characteristics of a GPU: many cores, high parallelism, right? Parallelism, high parallelism, high parallelism. A GPU has thousands of smaller, efficient cores optimized for simultaneous tasks, making it ideal for workloads like mstrix, matrix or matrix multiplications. Yeah, matrix. I think it's matrix. Let's check out the pronunciation, right? Matrix.
Matrix.
Exactly, or matrix, but matrix is more correct. Many cores, high parallelism. A GPU has thousands of smaller, efficient cores optimized for simultaneous tasks, making it ideal for workloads like matrix multiplications. High throughput, specialized for performing the same type of operation across large datasets in parallel. SIMD architecture uses a single instruction, multiple data processing, which excels at repetitive calculation. Strengths of a GPU, AI and machine learning speeds up training and inference for deep learning models. Graphics rendering, essential for gaming, 3D modeling, and visualization. Scientific computing accelerates simulations, data analysis, and high performance computing, HPC. Video processing, efficient for encoding, decoding, and real time video streaming. Limitations of a GPU, less effective at complex logic and sequential tasks compared to CPUs. Higher power consumption for continuous workloads. Needs a CPU to accommodate operations or coordinate operations, cannot replace a CPU entirely. Higher power consumption, right? Use cases of GPUs, gaming and graphics, rendering realistic 3D environments. AI and deep learning, here we go, training large-scale neural networks like LLMs, or image models. Data analytics and big data, processing huge data sets in parallel. Video streaming, hardware acceleration for encoding, decoding, NVMe, AMF, etc. What is a TPU, right? Google TPU, Alphabet company. Tensor processing unit. A TPU or tensor processing unit is a specialized processor developed by Google to accelerate machine learning workloads, especially deep learning models. Unlike CPUs, general purpose, and GPUs, parallel purpose, TPUs are application-specific integrated circuits, ASICs, right? ASICs, optimized for tensor operations, which are the core of neural network training and inference. Tension, right? Tensor. Key characteristics of a TPU, matrix multiply engine designed for faster tensor and matrix operations. Of course, matrix has rows and columns. Tensor, it's like a E over AX, right? Tensor. Tensor operations, for example, a real number plus I imaginary number. So, for example, 3 plus I4 or 4 plus I3 will have the amplitude of 5, right? It's more like a factor. Tensor operations make it easy to compute some repetitive, cyclic movement of some data, just like voltage of your AC current. Matrix multiply engine designed for fast tensor and matrix operations, optimized for AI built to handle the workloads of TensorFlow and other machine learning frameworks. High efficiency, high energy efficiency delivers more performance per watt for AI tasks compared to GPUs. Cloud-first design, widely available through Google Cloud rather than as consumer hardware. Strengths of a TPU: AI training and inference at scale, especially effective for large models like transformers and LLMs. Specialized hardware provides lower latency and higher throughput than GPUs for supported workloads. Scalability: TPUs are designed to run in pods, enabling massive parallel training. Scalability, right? Pods. Just like app, right? Or what they call container app, right? Container. Docker and Kubernetes. Limitations of a TPU: narrow focus, less flexible than GPUs, mainly optimized for deep learning rather than general HPC or graphics. Limited ecosystem, mostly tied to Google Cloud with less availability for on-premises use. Software dependency: performance best with TensorFlow, less mature support for other frameworks like PyTorch through improving. So it's a very specific Google supported applications, right? ASICs, chips, less flexible, right? But especially trained for AI. Use cases of TPUs: large-scale AI training massive language models, LLMs, and image models. AI inference in production, accelerating real-time predictions in cloud applications. Enterprise and research AI, used by companies and institutions for cutting-edge ML workloads. So not only Google uses it, but other large corporations or AI companies can use them, right? Obviously, they get supplies, TPU supplies from Google. A comparison of CPU versus GPU versus TPU. The image illustrates how memory design and compute primitives evolve from CPU to GPU, then TPU, to support increasingly parallel workloads from general-purpose computation scalar to deep learning specific tensor operations. So general-purpose computing is called a scalar, right? Tensor is like a vector, like a second degree. Scalar is just first degree. So GPUs and TPUs. Let's find out. Let's check out this photo, right? Memory subsystem architecture. This image captures the memory architecture of CPU, GPU, and TPU memory system architectures. CPU is well stocked, right? L3, L2, and L1D, L1I, L1D, L1I supports L2, and 2L2 support L3. Implicitly managed, GPU has a four-layer stack: L2, SM, L1/TX, and RF mixed. TPUs: activation buffer, that looks a bit strange, right? It's not well organized structure, but it's quite flexible and handy, light version. Activation buffer Weight, I think WGT means weight, right? Like weighted functions, different values to different variables. FIFO, first in, first out. Right? Accumulation, register file, explicitly managed. Compute primitive. This image summarizes the compute primitive, smallest unit in GPU, CPU, and TPU. CPU is a scalar, right? Vector, compute primitive vector. Vector is like a one row or one column or a sub part of column, but tensor is like a groups of columns, groups of rows. Interesting. Memory subsystem architecture. CPU features multiple cache levels, L1, L2, L3, that are implicitly managed by the hardware. L1 is split into instruction, L1I, and data, L1D caches. GPU uses a mixed memory management system with L1 caches per streaming, multiprocessor SM, shared memory, and register files RF. L2 cache acts as a higher level shared cache. TPU memory is explicitly managed with specialized buffers, activation buffer, weight FIFO, and accumulator register file optimized for matrix tensor computations. Compute primitives. CPU operates primarily on scalar units, executing one operation at a time. GPU uses vector units capable of processing multiple elements simultaneously in a SIMD fashion, right? Single instruction, multiple data fashion. Single instruction, multiple data fashion, SIMD. TPU operates on tensor units, processing large blocks of data matrix tensor operations in parallel, ideal for deep learning workloads. Right? Can regular hosting providers offer TPU hosting? Unlike GPUs, which can be purchased from vendors such as NVIDIA or AMD and installed into dedicated servers, TPUs are proprietary hardware developed and maintained by Google. This means that most traditional hosting providers cannot simply add TPU cards to their infrastructure and offer them as a service. Currently, TPU hosting is almost exclusively available through Google Cloud, where users can rent TPU v2, v3, v4, and the latest v5p models on demand. For hosting providers, the practical way to include TPU services is by partnering with Google Cloud and reselling or integrating TPU access into their own platforms. As a result, while GPU hosting is widely offered by many data centers and providers, TPU hosting remains highly specialized and limited to Google's ecosystem, making it less common in the broader hosting market. Interesting. For hosting providers like M3N networks, the practical way to include TPU services is by partnering with Google Cloud and reselling or integrating TPU access into their own platforms. Future trends, CPUs, they will continue to serve as the foundation for system control and general logic, but will play a more supporting role in AI training. Yeah, they have to, right? GPUs, they will remain the mainstream AI computing hardware, particularly in low-level machine learning, LLM, training, inference, rendering, and scientific computing, TPUs. They will continue to develop within the Google Cloud ecosystem while also inspiring innovation in more specialized AI chips such as NPUs, ASICs, and FPGAs, right? Within the Google Cloud ecosystem, while also inspiring innovation in more specialized AI chips such as NPUs, ASICs, FPGAs. Conclusion: CPUs, GPUs, and TPUs. CPUs, GPUs, and TPUs are different types of processors, each optimized for different computing tasks. CPUs are the most versatile, excelling at handling complex logic and multitasking. GPUs excel at massively parallel computing and are commonly used for graphics rendering and AI training. TPUs are optimized for deep learning, offering exceptional efficiency in matrix operations and AI inference. Each has its own focus, and most appropriate chip is typically chosen based on the task at hand, right? So CPUs are versatile and excelling at handling complex logic and multitasking. GPUs excel at massively parallel computing and are commonly used for graphics rendering. Yep, Studio Lennon, Lucas, and Ansys Lab, those are great companies in Korea doing the graphics rendering, 3D, 2D, whatever you want, right? They are graphics rendering company. And AI training, right? It's AI training, not AI inference. TPUs are optimized for deep learning, offering exceptional efficiency in matrix operations and AI inference, right? AI inference, not AI training, not repetitive, past-facing AI, but it's a future-facing AI inference and matrix operations. Each has its own focus, and the most appropriate chip is typically chosen based on the task at hand. This is good sentence, man. Each has its own focus. Each has its own focus. Each has its own focus, and the most appropriate chip is typically chosen based on the task at hand. Based on the task at hand. Based on the task at hand. Each has its own focus, and the most appropriate chip is typically chosen based on the task at hand. Each has its own focus, and the specific chip is chosen based on the based on the task at hand. Keywords. Okay, so this is a basic primer, a very easy to understand, succinct article, but it gives you a very summarized knowledge on CPUs, GPUs, and TPUs. From this article, we learned two expressions. Each has its own focus, and a specific chip is chosen based on the task at hand. Right, the most appropriate chip is chosen based on the task at hand. And what else I remembered? Right, what else? So we go back to the photos where I was told each has its own focus, and the most appropriate chip is typically chosen based on the task at hand. logic-heavy operations, right? Logic-heavy tasks, efficiently. Logic server-side tasks, public-facing, business-facing, internal, external, storefront, back-end, backhaul, right? Back-end, front-end, server-side, not customer-side, client-side, or logic-heavy tasks. Each has its own focus, and the most appropriate chip is chosen based on the task at hand. Thanks for listening and have a great Wednesday, hump day. Bye-bye.